Today we're going to talk about the interaction of folding and faulting, so two geologic structures that very commonly occur together. One of the really common types of faults we see a lot of are thrust faults, where we've had compression and a block of strata has pushed up and over another block. Now when that happens, the rocks in the hanging wall, as they move up the ramp, will become folded over on top. There's a couple terms that we can use for that. But if you look at it, we break it down, there's really several different types of folds there. For starters, we have a little bit of a syncline, which would be the leading edge syncline. Then we have the leading anticline. All right, those represent the areas above the fault, so in the hanging wall, that are out in front of the ramp. So that's as the rocks have pushed up and over, and they've reached to the top of the ramp in that second portion of that next level up flat. All right, so if we trace those dotted lines would be your fold axes. So we trace that down, where those strike down into the subsurface, those are going to be up at the upper portion of the ramp. They'll be up and off the ramp. All right, so we go back, and then there's this trailing anticline. The whole thing is one big anticline, sure. But if you break it down, there's two little fold components. This trailing anticline area, if we trace that down, that's going to hit right at the top of the ramp. Right, so if we use these orientations, which we can measure in the field, we can find the orientation and location of faults deep down. Now this is really critical because, let's go down here and look at this. We have this trailing syncline. All right, the trailing syncline back there, we trace that down, the axial trace of that, it's going to strike the base of the ramp. Now, what's important here is with ramps, those are conduits for fluids to move up and down. So it is really important to know not only where they are at the surface, where these faults hit the surface, but where they are deep down. That's in fact probably way more important than where a fault hits at the surface. So where is that fault structure, in this case the ramp, located at depth? Because, let's think contamination world. If we were to have some sort of spill at the surface, the contamination gets down. If we know where that ramp is, that represents a place for what we'd call vertical migration. Right? That would be the fluid can move down and vertically move deeper into the subsurface. So if we had multiple aquifers, the upper aquifer may be contaminated, and if we're in the wrong spot, near one of these ramps, that may be a location where fluids can move and get into a lower aquifer. And so that would be a scenario where knowing the location and orientation and character of this fault would be really critical to preventing subsurface migration of contaminants. You want to think oil and gas, it's just upside down. This would represent a location where you might have vertical migration of hydrocarbons moving up, moving into the ramp of the thrust fault, moving up to higher levels. In fact, in this case, not only moving up, but moving up and over, running along the fault potentially. There's a lot of variables there, but that whole concept of what does the thrust fault look like at depth, where exactly is it, these are critical for any sort of subsurface work we're doing where we have thrust faults. Immediately, what pops to mind when I think of thrust faults is Appalachians, right? This is the majority of the Appalachians are these big thrust fault structures. This is the dominant architectural feature you're going to see, these ramp thrust fault systems. So really important if you're working East Coast. West Coast as well, too. Out there would be called the severe origin stuff. So you have the same rocks out, more or less on the western side of the Rockies. These structures kick back up, but they can pretty much be found anywhere. There's even a handful of little thrust fault systems like this here in Missouri, middle of nowhere. So you're going to see these anywhere you go. But these are dominant structures in the eastern United States. Appalachians, this would be the Appalachian Valley and Ridge, is a textbook example of these thrust faults. Thinking about that character of these relationships, one really important component is to figure out how much displacement has occurred along the fault. Because a lot of displacement, huge hundreds of feet of displacement, you think about those rocks kind of grinding against each other, ablating all the material down, that's more likely to give you fault gouge, which is fine-grained mud component along a fault. Fault gouge is less likely to let fluids move along it. So we're talking about these faults as conduits for fluids. Fault gouge is going to be less likely to let fluids move along a fault, whereas a fault breccia, which is just broken rocks, just like a sedimentary breccia along a fault, is more common going to occur in lower displacement areas. So one thing is important is to estimate the amount of offset. We can do that if we can see some sort of subsurface information, the subsurface architecture. In this case, a cross-section would answer that question. If we're looking at this, what we try to find is the hanging wall and the footwall cutoffs. Now, we get to define what that is. The best way to do that is to find a marker bed that you're really clear on. So if you're working on seismic data, you're looking for a real clear indicator on the seismic data that goes across the fault. If you're dealing with a cross-section, whatever unit you feel confident with. But you find one rock horizon in the hanging wall, and then you find the identical horizon in the footwall. I did that backwards with my hands, but whatever. Hanging wall cut off here, footwall cut off there. And then you can measure the amount of offset between the hanging wall and footwall cutoff. These are also important if we're trying to reconstruct everything. We would then take the hanging wall cutoff and move it back down and line it up with the footwall cutoff, and we can build what's called a reconstruction. In fact, the term for it is called a palinspastic reconstruction, where we can build back how much these rocks have moved together and how much movement has occurred. These are really critical, too, in paleogeographic reconstructions. If we're trying to figure out how big an area was before it got compressed, this is the way to do it. So it would be like taking a aluminum can that has been squished and then stretching it back out. We're just doing that with strata. When we see these folds at the top, those are called fault bend folds. This is a different type of structure called a fault propagation fold. And so there's a couple terms for these, snakehead folds, sometimes a term. But when a thrust fault pushes up and it pushes the rocks above up and kind of kinks them up on top, a lot of times that fault doesn't break all the way through to the surface. So the term fault propagation fold is the fold is occurring because the fault is propagating upward in the strata. So deeper down, the compression is accommodated by faulting. The rocks push up and over, but closer to the surface where there's room to bow up, if you want to think of it that way, the rocks are able to fold up and over because it's much easier and the fault hasn't broken through to the surface. So another term for this would be a blind thrust. Again, really important because this is a vertical migration pathway deep down in the subsurface, and we see the fold at the surface. So if we see a fold, we can interpret the location of that vertical migration pathway at depth. Now, you might ask, the other fault didn't seem to break through to the surface, right? But it did come up and kept going. Those faults, the fault bend fold, usually will come up, the ramp kicks up, and then it goes flat again. Ultimately, that will kick up to the surface and make it to the surface. Most of the time, you'll see those at the surface. Normal faults are not immune to folds as well. And so here's a nice example of a normal fault. This would be a listric normal fault. It's kind of got a curved surface. And so the hanging wall has dropped down. And what it creates is an anticlinal structure that we call a rollover anticline. As the rocks move down the listric curved surface, they create the anticline. And what's really cool about this figure, if you see the yellow here, these are called growth strata. This is what happens when you start to drop one block down. If you think about your sedimentology terms, one of them is the term accommodation, which is space to put sediment. When you have the hanging wall drop, you've created accommodation above the hanging wall. And when that happens, if this is subaerially exposed, then you get erosion on both sides that starts to fill in. And you'll actually see that they thicken towards the scarp of the fault and thin away because there's more accommodation as that hanging wall slips down. So those are called growth strata, and they're really common in fault-controlled basins. You can also get what are called detachment folds. These are really wild. So if you have a detachment fault or a décollement at depth, the rocks above are detached from everything beneath that fault surface. And so the way to think about this is kind of like a rug. And so if you slip on the rug a little bit, it can kink up and create the fold at the surface. This is not like a fault bend fold. The fault's not going up. This is not a fault propagation fold. Same. The fault's not moving up through the strata. The fault is horizontal, allowing the rocks on top to squish and kind of fold up. And so you've got a couple different types of geometries, but those are called detachment folding. And they occur above flat areas in a detachment fault. What defines whether a rock folds or faults is really interesting. And so we like to think about the term mechanical stratigraphy. Mechanical stratigraphy you can think about as what are the mechanical properties of the strata based on their lithology. So example, chert. Chert is very hard. It is very brittle, has very high strength. So chert doesn't fold very easily. It can totally fold, but it is also probably going to be accompanied with a lot of fracturing if you try to fold a chert. So think about trying to fold a piece of chocolate, right? As soon as you start trying to bend it, it's just going to break. Now you can turn the two bars of chocolate like they're folded, but right in the middle where that fold is, they're going to be broken in half. All right, compare that to like a shale. That would be more or less like Play-Doh. Play-Doh is a good shale correlative. If I was to make a little thin thing of Play-Doh, I could easily bend that. So imagine stacking chocolate, Play-Doh, and then bending and trying to fold that. The chocolate is going to behave different than the Play-Doh. I don't know why I used food items mixed with non-food items. I got to think of a better analog for Play-Doh that you can eat that is delicious. But that holds. How about a s'more? Let's use a s'more. Graham cracker, hard, right? Gonna break. Kind of warm chocolate, still probably gonna break. Gooey marshmallow, right? Stack it on top, bend it. The gooey marshmallow will plastically bend. The stuff around it will fracture and break, even though I can still fold the s'more in half. Right? I'm going to have fracturing along there. That's a good example of mechanical stratigraphy, where how the rocks behave is directly correlated with their physical properties. Salt is a geologic resource we don't generally talk too much about. It's huge in the energy industry. It's massive oil and gas deposits associated with salt. That's just one. Salt by itself is also a geologic resource. So how salt behaves when we start thinking about mechanical stratigraphy, salt is kind of on its own in the fact that it doesn't really behave like a rock. It almost has its own kind of set of behaviors in the fact that it's much lower density than other rocks, and it's very squishy. You get salt a little bit warm and put a little bit of pressure, and it is going to behave like what's called a diapir, right? That's how lava lamps work. Think of a lava lamp, those big blurbs going up. You have a small density difference. You have a material that's able to move up, and the little lava blurbs go towards the surface. That's how salt behaves. And so if you have this salt layer at depth, you start to heat it up, have all this pressure, it's able to start moving up, and it will deform the rocks above it, creating folds, faults. The overlying strata, if the salt moves, will then slump down and create folding and faulting above where the salt used to be and has now squished out somewhere else. The whole stack of rocks on top can kind of slide on the salt too because it's such a weak rock. The term that gets used a lot is called salt tectonics because it kind of behaves in its own way, right? Low density stuff moving up. And you can see on the edges, you get these kind of turned up little synclines because the salt is just bullying its way through the overlying strata because of its low density. All right. It's also kind of what we call self-annealing, or the salt will recrystallize back together. So it has no fractures in it because it can't break. It's just squishing. It's Play-Doh, right? Sliding up. So what that means is right along the sides here, if you have some sort of fluids moving and they're trying to move up, they'll go up here, they'll hit something they can't move through, they'll go laterally, they hit the salt, and then they're stuck along the edges of the salt. That's the basis of what are called salt plays in the energy industry, right? So, in fact, a better term is monocline here. You get these kind of monoclinal or synclinal structures right on the edge that are associated with the salt. My favorite example is the Gulf of Mexico. Look at these. These round areas, these are salt diapirs getting to the surface. This is right off the shore of the Florida Panhandle, Alabama, Gulf Coast, Orange Beach kind of area. Right off shore, I don't know, tens of miles, you have these areas where these round structures are the salt diapirs making it to the surface, or creating these salt domes. And then once they hit the surface, the water is able to dissolve the salt back into solution, and you get these round structures. Now over here, this is off the coast of Louisiana, Texas. You can see this almost looks, it's an escarpment, but it looks like it's almost like a trench, like a subsea trench where you have subduction, but it's not. It's all these rocks over here sliding and pushing forward because they're on a layer of salt, Play-Doh, right? And the weight of the rocks is squishing down as they kind of slide off. You can also see all these kind of mud crack looking features. That's where the salt is being mobilized and they're slumping down on top. So the fact that you've got salt at depth is creating all these different complex structures that are right at the surface. All right. So once we've had structures, Another way to get folding is through reactivation, right? So faults aren't necessarily the end all be all. Once a structure occurs, it can be later reactivated. And so here's an example. You get some compression, you can get folding, a little bit of faulting develop there, then everything kind of pulls apart. You can get normal faulting down. You reapply those stresses back and forth, which is really common. Remember the Wilson cycle where we pull continents apart and push them back together? So we're just kind of slamming things together, pulling them apart, slamming things together, and pulling them apart again. And so when that happens, you have reactivation of structures. That's really common. And so when that happens, you can start to see bowing up along. Here's a normal fault that has been reactivated into a reverse fault and kind of bowed up at the top, and you get that additional folding. Right? That's really common. And a good example of reactivation is the mid-continental New Madrid seismic zone. So we got a lot of questions about this one here in Missouri. This pops up. People go, what about New Madrid? Well, New Madrid is this seismic zone, somewhat known because in the early 19th century, there were a series of very strong magnitude earthquakes. There were not a lot of folks living out here, but these earthquakes were felt as far over as the East Coast. Very massive earthquakes. And there's still some seismicity now to this day. And that's a good example, though, of a reactivation, where a structure exists, it's been there for a very long time, and it has been repeatedly reactivated. And so if you were to go down beneath the New Madrid and be able to dissect where all the faults were, deep underneath, say, Memphis, Tennessee, the Mississippi River, you would find some faults that are well over 500 million years old. Very old, billion-year-old basement rocks down there, billion-year-old or older basement rocks. Then those are structures down there. About 500 million years ago, this area tried to exploit those structures and rip itself apart. That's called the Real Foot Rift. It failed. It did not rift. The continent obviously did not rift, right? Because Missouri is still touching Illinois. Otherwise, those would have ripped right apart. But it tried to rip itself apart. It failed, and it created a lot more structures associated with that, trying to rip the continent apart. All right, then fast forward a little bit into the Cretaceous, so about, 100 to 75 million years ago, that area becomes active again, moving around. In fact, very specifically, it looks like it moved up and then was eroded away and then dropped down again. All right, so that area is bouncing up, bouncing down, and currently that's where the Mississippi River runs through that exact area, because that area has been moving up and down, reactivating those structures that were reactivated 500 million years ago that are even much older than that. Okay, now in the modern era, now like early 19th century, recorded human history, not that long ago, these faults were moving around again, creating those massive earthquakes in the New Madrid seismic zone. So that's a good example of, you've had well over 1 billion plus years of geologic history that have accumulated that are still reactivating these broken areas. So once you've broken rocks, they remain broken and they remain a weak spot. So if you apply stresses again, whether you're compressing or pulling apart, rocks are going to be prone to fail and fault or fold and deform at the places where they've already faulted and folded and deformed before.